So in order to begin understanding antimatter and that strange idea, we have to understand that all matter, like quarks, that contain quarks, baryons, have opposite mirror images called anti-quarks, antimatter. Okay, so if I make matter with quarks, but instead of the quarks I'm using anti-quarks, I'm going to be inferring the opposite properties. So for every single one of these quarks, up, down, charm, strange, top, and bottom, I have the anti-quark, okay, that exists in nature. And an anti-up, that symbol with that bar on top, means anti, okay? Just like in nuclear physics, you talked about anti-neutrinos that had a bar on top. So anything that has a bar on top is the antiparticle, and it had the opposite property. So anti-up would be negative 1/2 spin, negative 2/3 charged, okay? So it would infer the opposite properties, all right? So it just gives it that negative sign for there, okay? Unlike the down anti-quark would have a positive 1/3 charge and a negative 1/2 spin, okay? So any particle that has an anti is just the opposite properties. So let's take a look at, for example, the anti-up quark, the charge would be negative 2/3. The anti-charm quark, charm is here, would be negative 2/3. And the anti-strange quark would be positive 1/3. Okay, that would be the properties of those particles. So how do we predict the charge of a baryon? So to remember what a baryon is any particle in the atom that contains 3 quarks. So to determine the overall charge of a particle that contains 3 quarks, such as a proton, I have to take a look at that table. So a neutron contains up, down, down, okay? That's the combination of quarks. So if I go back up to this table, I can see the up is 2/3, down is negative 1/3. So positive 2/3, negative 1/3, negative 1/3. If I add that all together, the total charge is 0, okay? Now, the anti-neutron would be made of the anti-quark. So anti-up, which would be negative 2/3, and then anti-down, which is positive 1/3, and the anti-down is positive 1/3. You sum that up, and I would have a total net charge of 0. Okay. Now, if I look at a proton has an up quark, and a down quark. If I sum that all up together, the net charge is positive 1. And if I look at the antiproton, negative 2/3, positive 1/3, sum that all up together, the net charge is negative 1. Okay, that explains that. So a neutron and an antineutron don't have any differences, but a proton and an antiproton have opposite charges. Okay, and that's by the nature of the quarks and how they change the charge and the properties. Okay, so to remember, a baryon is any particle in the atom that contains 3 quarks, and baryons also have a number. Okay, so each quark also, in addition to charge and all that other stuff, has baryon numbers. So all quarks have a baryon number of positive 1/3. This is probably all starting to get pretty frustrating and confusing for you. There's a lot of numbers and names. In your data booklet, I want you guys to right now stop and open up the data booklet and search for nuclear physics, and you would see a table in there that has all these names and values in there for you. So you don't have to memorize any of this stuff. All the charges, the baryon numbers, it's all there. So you can always just refer to that table, and if they ask you to calculate the baryon number or the charge of that combination, you'd be able to just remember, okay, the numbers are in the table, I put it down and I add it up, and it should be pretty straightforward. So you just have to do a few problems in SOCOS and the test yourself questions, and you'd be ready to do this on an exam. So all quarks have a baryon number of positive 1/3, and all anti-quarks have a baryon number of negative 1/3. All right, so if I add up the baryon number of a proton, okay, each of them has 1/3, 1/3 plus 1/3 plus 1/3. A proton has a baryon number of 1, which means that it's a baryon that exists in the nucleus. Antiquarks have a baryon number of negative 1/3. So if you added that up, it would be a negative 1 baryon number. It means that it exists in the nucleus, but it's an antimatter. Okay, so baryons are particles found in the nucleus, such as protons and neutrons, which have a baryon number of 1. To determine it, again, you just put the baryon number of each quark, add it up. Protons have a baryon number of 1. Neutrons have a baryon number of 1. Okay, and the antiproton, which has a negative 1/3 baryon number, has a baryon number of -1. This will become important when we start talking about nuclear reactions where neutrons are converted into protons. There are some rules of tracking that are involved. Okay, mesons are another type of particle that we talked about before. They're exchange particles. They're not in the nucleus, but they mediate forces. Mesons contain 2 quarks and have a baryon number of 0 because they don't exist in the nucleus. So in order for that to happen, the quark combination has to be a normal quark and an anti-quark so that the baryon numbers cancel out. So 1/3 plus -1/3, the baryon number is 0. It does not exist in the nucleus. It is an exchange particle. Baryon number has to be 0. Okay? So all mesons, all force mediating particles contain 2 quarks, a positive quark and an anti-quark combination. Mesons always have that combination, all right? And their baryon number has to be 0. All right, we'll continue with reactions in a second.